আমরা যেটা পড়ছিলাম sol gel method to prepare a nanomaterial. Sol gel method, it is a bottom up process. Bottom up process means from lower to higher. From we first prepare the molecule, and from molecule to the nanomolecule. That means molecules with nano-sized. So it is economically viable, very much. Also, it is very popular method to prepare a nanomaterial or a nanoparticle. There are many substances which can be prepared by sol gel methods. The main theory of sol gel method is to first prepare a sol, then allow it to produce a gel, and to dry the gel to form aerogel or to form aerogel, depending on the drying process. And from that sol gel method, we can prepare the nanomaterial from the sol also. We can prepare thin films of nanomaterial from sols, or we can draw fiber from sols, or we can prepare nano powder from sols also, which we can prepare from gels also. So, as because this process is very much important, we shall see some details of every part of this process. Now, there are generally 4 steps of sol gel process. First one is hydrolysis, and second one is condensation. This hydrolysis and condensations occurs simultaneously. First hydrolysis and then condensation. I have shown you a reaction. This is the reaction. This is hydrolysis. Hydrolysis means to form, this is alkoxy group, which is it may be a methoxy group or ethoxy group. That means if it is methoxy group, then the name of this compound is tetramethoxysilane. The name of this group is tetramethoxysilane. If it is a ethoxy group, then the name of this compound is tetraethoxysilane. We told you the precursor will be an alkoxy group or an metal chloride or a metal chloride. Now, to prepare silica gel, actually, silica gel means a gel with a silicon. To prepare silica gel, it is a widely used gel. To prepare silica gel, we can use tetraethoxy or tetramethoxysilane as precursor. Then we hydrolyze it to form an alcoholic group in place of a methyl group or ethyl group. This is the alcohol, and an alcohol is going out. Now, this is the hydrolysis portion, and the condensation portion is it can be the condensation is done in 2 ways. First one, 2 of this alcohol can be condensed, or 1 alcohol molecule and 1 alkoxy molecule, that means tetraethoxy or tetramethoxy group, tetramethoxy silane can be condensed. So here there are two alcoholic silanes are condensed. Uh, it 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 Water comes out from this condensation reaction, and here alcohol comes out from this condensation reaction. In both cases, the compound is same. This is the sol. Actually, this is the sol, and and it becomes a gel by the condensation. This molecule contains with another molecule and to form a three-dimensional structure, which is known as gel. Now, this is the basic reaction of your sol gel formation. Now, to go to the details, first we have to see what is a sol. What is a sol? So, a sol actually consists of a liquid with colloidal particles which are not dissolved. There is a liquid, it may be water or any other solvent, and a small colloidal particle that is not dissolved in the liquid, but it will not precipitate also. That colloidal particle is so small and so light that gravitational forces will not act on this your particle, and it will not precipitate or it will not get sedimented. Now, another thing is that agglomeration. Agglomeration means one of that particle is agglomerated, attached with other that particle to form a big molecule. One small sol, one small sol agglomerated with other small sol to form a big molecule. That is called agglomeration or coagulation, whatever you can say. So we have to prevent that agglomeration, because if agglomeration happens, one particle comes in touch with another particle, then we'll get a big size particle, which will not be a nanoparticle. So our view is to prevent the agglomeration. So why agglomeration is done? Agglomeration of small particles are due to van der Waals forces. Agglomeration of small particles, these small particles, it was occurred due to van der Waals forces between the two particles, between the atoms of two particles. because the particle actually, if they are free, if the particles are free, their surface energy is high. If they are agglomerated, then their surface energy will be reduced. So to reduce the surface energy, particle wants to agglomerate with themselves. But what happens? I think you have studied in your fourth year physical chemistry. In a sol, there is a electrical layer outside the sol. We call them an electrical double layer. What happens in a sol? Some ionic particle is absorbed at the surface of the sol. Say, for example, some cationic particles from the solvent is absorbed on the surface of that particle. So the particle becomes ionized. Say, for example, the particle becomes positively charged ionized. Now, another particle that is also positively charged. So if two particles comes to agglomerate, this this positive charge of one particle and positive charge of another particle will repulse each other and prevent the agglomeration. Agglomeration is due to the attraction by the van der Waals forces. Say, for example, this particle attracts this particle by van der Waals forces. So attraction happens, but due to the repulsion of same charges, which is on the adhesion of the positively charged particle particle on a salt surface, which is due to the adhesion of the positively charged particle on the salt surface, that becomes a repulsion which prevents the agglomeration. So we have to establish that repulsion. We have to see that this repulsion is maintained. We have to see the established of this repulsion. Otherwise, agglomeration will happen. We shall not get any of your nanomaterial. We will get a bulk material. So what they tells us that agglomeration of small particles are due to van der Waals forces and a tendency to decrease the total surface energy. This agglomeration actually decreases the total surface energy, and for that agglomeration is happened. Agglomeration happened. Van der Waals forces are weak and extend only for a few nanometers. In order to counter this van der Waals interaction, repulsive forces must be established. In order to counter this attraction, some repulsive forces must be established. What are that repulsive forces? I told you now, electrostatic repulsion by adsorption of charged species on the surface of the particles. That means on the surface of the salt particle, some charged particle is absorbed, and this charged particle repulses another salt molecule and prevents the agglomeration. Repulsion between the particle will increase and agglomeration will be prevented. This is most important for the colloidal system. This is most important for the colloidal system. As because this repulsion happens in a sol, so we shall take the route of sol-gel process to prepare the nanomaterial. Normal precipitation, say for example, you have prepared or we can precipitate silver, any chloride, say for example sodium chloride. If you give silver nitrate there, you will get precipitate of silver chloride. But no sol is produced there. For that, we shall get a bulk molecule, not a nanomolecule, not a nano-sized molecule. We generally get bulk molecule. So to get a nano-sized molecule, we have to prepare the sol first. Why sol is prepared? Because one sol repulses the other salt so that no agglomeration or no coagulation is occurred, and we shall get a nanomaterial. So salt production is very much important here. If you don't, if you do not able to produce salt in any solution, then you will not actually get the nanomaterial at all. Now, this is the first thing, electrostatic repulsion. Now, there are another case also. There are another type of thing happens. Sometimes what happens, say for example, this is a salt particle or this is a salt particle, an organic layer, uh, mm, an organic layer actually absorbed to the surface of the salt particle. This is an organic layer. Organic layer means layer of organic compounds. So that this is a inert organic layer and this is also inert organic layer. They cannot attract each other and so they become separated. By absorbing a thick layer of organic molecules, the salt particle absorbed thick layer of organic molecules. A thick layer of organic molecules, they absorb a thick layer of organic molecules from where? From the solution. They absorb a thick layer of the organic molecule. And as because this is an inert layer and this is also inert layer, Van der Waals force cannot your attract these materials, these salt particles, and they become separated. So this is another type of procedure where the nanoparticles are separated by themselves. So the production of salt, is very much important to prepare this sol gel method. Now, next one is coagulation. Coagulation means this type of condensation. Many salt molecules attracted each other to form a big molecule. This is another type of here attraction, which is called coagulation. Why coagulation of salt occurs? The surface potential is lowered by changing pH by increasing the number of counter ions. The surface potential means the salt has a surface, I told you, and it absorbs a charged particle, charged ion. For that, one salt repels other salt. Now, but if by any means this charge, the potential means the amount of charge, if by any means the amount of charge becomes low, then attraction between two salt molecules happens and it coagulated. Now, how we can this surface potential is lowered? If you lower the pH or if you higher the pH, then what happened? Say for example, there are some positive charges in the salt molecule. Lowering or higher pH means you are adding some positive ion or you are withdrawing some positive ion from the solution. Lowering or higher of pH means that you are adding Lowering of pH means you are adding some positive ions. Say, for example, you are adding some hydrogen ion there, or you are adding some hydroxyl ion there. So if you add some hydroxyl ion there, for example, if you add some negative ion there, then the negative ion will lower the uh, positive charge of the surface of the salt, because the negative charge increases. The negative charge increases means it will react with the positive charge, and thus on the surface of the salt molecule, the surface potential becomes lowered. That means amount of positive charge on the surface of the salt will be less due to the reaction with negative charge, that means hydroxyl ion. So if the surface charge will be less, if the surface charge is less, now the salt molecule is free, and it will attract another salt molecule to coagulate, to attach with each other, because there will be a less repulsion, because in the surface there are a small amount of positive charge, and here there are a small amount of positive charge. So less repulsion, there will be a less repulsion, and coagulation happens. So the surface potential, that is adjusting of pH, is very much important. Adjusting of pH is very much important. Now, now how to adjust the pH? Okay, you'll see when salt is formed by this pH, or by this pH, the more salt is formed by pH 5, or you have to see by pH 3, the more and more salt is formed. Okay, you have many processes to adjust the pH, but you have to adjust the pH. You have to adjust the pH to prevent the coagulation or agglomeration. Now, an increase of concentration of counter ion results a decrease of the thickness of the double layer. That means, what do you mean by counter ion? Counter ion means the salt surface has one type of ion. Say, for example, the salt surface has positive ion, and an increase of negative ion in the solution decrease the thickness of the double layer. That means the layer of charges in the salt solution. Why double layer? You know, in a colloid or in a salt substance, there is a layer of positive charge, and this positively charged layer will attract another negatively charged layer to form a double layer. Now, in some cases, the coagulated colloid may be dispersed. If by any means the coagulation happens, it may be dispersed in some cases. That is called peptizing. How this is done? That is done by removing the surplus counter ions by washing or adding by adding charged ion. You have given or some counter ion is produced there. Some negative charge is produced there, which just lowers the surface potential of the salt. Now you have given or you have washed the surface of the salt, or you have given more positive ions in the solution from outside. Then the coagulated colloid becomes a coagulated colloid can be redispersed. Coagulation happened by the lowering of surface potential, but you have given some counter ion from outside, some positive ions, for example, from outside, so that it becomes redispersed. That is this is anticoagulation. That is anticoagulation actually. Now, this is the salt formation. This is the salt formation. Now, after salt formation, gel formation occurred. What is gel? Gel is the three-dimensional structure of salt. It is a three-dimensional structure of salt. So what is the gel point? Gel point is starting the formation of gel. The point at which the gel formation starts, that is known as gel point. Now, gel formation starts here. We call it gel point. But in a gel point, there is a large number of salt. But somewhere in a region, gelling is started. Somewhere in a region, gelling is started. So this is the gel point. This is the gel point. Now, after gelling started, what you have to do? You have to wait and see. You have to do nothing. You have to wait. Give time to formation of gel in the whole area. That is called aging. That is called aging. If you wait for a stipulated amount of time, what will happen? As the viscosity increases rapidly, because when gel formation starts, viscosity of the solution increases rapidly, and this solvent is trapped inside the gel. Gel is a three-dimensional structure, and solvent is trapped inside the gel. The structure may change considerably with time depending on pH, temperature, and the solvent. The structure of that gel, of that three-dimensional structure, changes depending on pH of the solution, temperature of the solution, and the nature of the solvent. The nature of the solvent means either the solvent is water, or the solvent is alcohol, or you can use any other solvent. The gel is still alive. The gel is still alive means the gel is still forming. In the time of aging, the gel is still forming. Actually, from a start of gel point, that means start of forming gel, to the up to the last formation of gel, the time is aging. The liquid phase still contains salt particle and it agglomerates, which will continue to react and will condense as gel dries. Now, when gel dries, the salt particle will agglomerate and they continue to react. They continue to react. The gel is originally flexible. Groups on neighboring branches will condense, make the gel even more viscous. Originally, the gel is flexible. That means the structure of gel can be changed. it is the structure. Say for example, after some time it becomes this way, after some time this becomes this way. The structure of gel can be changed. But as more and more condensation occurs, the gel becomes more viscous, and this will squeeze out the liquid from the interior of the gel. As more condensation occurs, liquid will evaporate, or liquid will be out from the three-dimensional structure of the gel. Hydrolysis and condensation are reversible process, and the material from thermodynamically unfavorable point will dissolve and precipitate at more favorable points. This is about hydrolysis and condensation of the salt particle. Now, after the gel formation, the next step is drying of gel. What is the drying of gel? Drying of gel means removal of liquid, or removal of solvent, or removal of byproducts from the gel. Removal of byproducts from the gel. So if you remove the liquid from a three-dimensional structure, say for example, this is a three-dimensional structure. Inside this structure, there are liquids. Now, if you remove this liquid, then what will happen with this structure? It may happen that air will replace that liquid. Air will replace that liquid. Or this three-dimensional structure may be collapsed. In a gel, it must have a three-dimensional structure. And inside the three-dimensional structure, there are some liquids. Now, when you start drying your gel, that means drying of gel means you have to remove the liquid inside the three-dimensional structure. Now, if you remove the liquid from the three-dimensional structure, then two things can happen. One is that air can replace the liquid, or this three-dimensional structure can collapse due to the empty space inside them. So if you normally dry the gel, means if you calcine the gel, then what will happen? This three-dimensional structure will collapse. Air cannot replace this space. The three-dimensional structure will collapse. Then we call it gel. When the three-dimensional structure of a gel is collapsed, then we call the gel as gel. But if air is there, if air replaces the solvent, then the three-dimensional network will not collapse, and we call this structure of gel as aerogel. So there are two types of gel. one is aerogel, and one is aerogel. Obviously, the aerogel will be more condensed because there is no air inside it, and the aerogel will be a porous, flappy substance. Aerogel will be a porous, flappy substance. So when we when that in the time of drying, actually in the time of drying, there are some reactions occur because when it collapses, the molecules comes closer together, and some reactions may happen there also. Some reactions may happen there also. What are the reactions? Which group on opposite sides may react and form a new bonds by condensation? Cracking may occur when tension in the gel is so large that it cannot shrink anymore. This type of reaction can happen. Gas will enter in the pore of a thin film of a liquid on the walls. So some reactions or some changes in physical properties occur in the time of drying. So aerogel actually occurs when there is one type of drying known as supercritical drying. Supercritical drying means it is the drying is performed inside a autoclave. This is a special type of drying where air replaces the solvent. This is special type of drying. So we'll not go to the details to that type of drying, but you have to know that it is a supercritical drying. So aerogel and aerogel, we can get aerogel and aerogel in the drying time of drying the gel. Now about the precursors. How we get the precursors. Actually, the precursors are mainly metal alkoxides and metal chlorides. Why they are used as precursors? Because they readily react with water. That means in water medium, they reacts. Now, I have told you about the precursors previously. Now, there are another way of synthesis nanomaterial in a sol-gel process. It is the polymeric route. That means polymerization occurs in the time of gel formation. That means polymerization forms the gel. Polymerization occurs in the time of gel formation. How it is formed? Say, for example, let us consider a process of synthesis by polymeric citrate process. How it is done? Polymer of ethylene glycol and titanium isoproposite are used as precursor. White precipitate seen on addition of citric acid. Say this is A and this is B. White precipitate seen in the addition of citric acid. Clear solution on dissolving all the reactants at room temperature. First white precipitate, you will see white precipitate, then you will get a clear solution when it dissolves in the room temperature. Then you will get a polymeric sol. The sol is a polymer. And if you heat it at 135 degrees centigrade, the salt becomes a gel. And after that, at 300 degrees centigrade, you will get the, about 500 degrees centigrade, you will get the product. So there are two OS. One is colloidal route, which we have discussed previously, and one is polymeric route, which we have discussed now. There are two routes to form a, a gel. In the polymeric route, you will get a polymer sol and you will get a polymer gel. And in the colloidal route, you will get colloidal sol and you will get colloidal gel. And in the time of drying, both of these will give you the same product. Both of these will give you colloidal gel and polymeric gel. In the time of drying, both of that will give you the same product. So you can get two routes. If you use the polymer sol, then you will get polymer gel. If you use the colloidal sol, then you will get colloidal gel. But when you dry it, when you dry this gel, you will eventually you will get the same product, whatever you want. Now, what are the difference between polymeric colloidal route versus polymeric route? You see, in colloidal route, you can use metal alkoxide or metal salt. We told you can use metal chloride as a precursor. But in polymeric route, you have to use metal alkoxide only. If you use metal chloride, it will not polymerize. Second thing, in the colloidal route, you can use solvent, alcohol, or water. You can use alcoholic solvent or water. But in the polymeric route, you have to use only alcohol solvent. Water solvent will not polymerization. Now, next one is formation of sol. Formation of sol. Here, alkoxide, the amount of alkoxide is much less than water. But in the polymeric route, water and alkoxide ratio will be 1:4. You have to keep the water or alkoxide ratio 1:4. Colloids are in aqueous medium. Here, inorganic polymer is formed. That means salts are in aqueous medium. In polymeric route, inorganic polymer is formed. Agglomeration are prevented by particle repulsion, which I have told you. But in the polymeric route, agglomeration is prevented by small size. The polymer has a small size. It do not absorb the positive or negative charges. So the agglomeration, it is so small that agglomeration will not occur there. Gel is a result of electrostatic effect. Gel is the result of further polymerization. Here, gel is the result of electrostatic effect. Gelling occurs, one sol attracts another sol. For that, gelling occurs. But here, gel is the result of further polymerization. A polymer makes further polymerization, then further polymerization occurs, gel occurs. Here the sol is crystalline, but here the sol is amorphous, and it is a microporous system. These are the polymeric route. Now this is the same reaction of your first. This is hydrolysis. This is hydrolysis, and after hydrolysis, these are the condensation reactions. Now this is the example. This slide we see the example of a substance, titanium. That means titanium oxide, sol gel synthesis. How you prepare a titanium dioxide, your nanoparticle. So you have to first take first the precursor titanium isopropoxide in isopropanol and solution of water and isopropanol. So what you have taken, a precursor titanium isopropoxide, we have taken here, you see, silicon methoxide, what you call tetramethoxysilicon, and in case of titanium, you can use isopropoxide in isopropanol. Solvent is also water is also taken in isopropanol. If you mix them, hydrolysis and condensation both forms. Hydrolysis and condensation both forms. Then filtration and washing to remove alcohol. Then you add nitric acid for stabilization, peptidization at 80-100 degrees centigrade. You know what is peptidization. Then you will get stable cell, and from that stable cell, we get your gel, and you will find titanium dioxide after calcining. Now, this calcination, that means temperature of this calcination, you will get at 300 degrees centigrade, you will get 20 nanometer your titanium. If you heat it 600 degrees centigrade during the time of calcination, you will get 50 nanometer size of titanium. These are called honest anatase and honest rutile form of titanium. You can see it here. First, you see the procedure here. This is the here is 6 ml of isopropanol with water, and here it is titanium isopropoxide. You'll add titanium isopropanol and titanium isopropoxide here, and add dropwise dilute distilled water about 75 ml. After adding water and 80 degrees centigrade, 1 hour stirring, you will get this type of substance. Then you will give acetic acid and nitric acid here. Then naturally cool and vacuum dry, you will get titanium dioxide nanoparticle. These are the plain procedure of a sol gel formation. Now, this is the reaction of this this titanium formation. This is the titanium isopropoxide, and this is the alcohol formation, and these two alcohol condense to form this sol, and after your drying, you will get titanium dioxide from this sol. And this is the condensation. You see here the temperature of calcination, that means temperature of drying, makes three type of titanium dioxide. One is anatase. This is the structure of anatase. This is the structure of rutile type of titanium dioxide. This is the structure of bruchite type of titanium dioxide. So on the basis of the temperature of the calcination, you will get different type of titanium dioxide nanoparticle. And last of all, the advantages and disadvantages. That means the advantages, it can be a low temperature route, uniform public size distributions occurs here, particle size distributions occurs there, provides good homogeneity, concentration of metals in the coatings can be controlled to these, chemical purity of nanocomposite, we will get pure chemical here. But there are some drawbacks. What are the drawbacks? A high cost of majority alkoxide precursors, say titanium isopropoxide or tetramethoxysilane. They are very costly, and it has a long processing time. These are the advantages and disadvantages of your sol-gel technique. And the control parameters of sol-gel techniques are the precursors, concentration of metal salt, temperature, catalyst, pH. That are the control temperature which I have discussed. So this is the sol-gel process actually. I have discussed in very details to you because this is the most popular method of preparing your nanoparticle. You will get powder nanoparticle in powder form. You will get nanoparticle in film form. You will get nanoparticle in sintered form. Actually, you will get nanoparticle in various ways in the sol-gel method. So it is very much important for us. And the next process is the vapor deposition process. We'll discuss it in the next class because if I start it now, I cannot complete it. So we shall discuss it in the next class, vapor deposition process. This is another important process. Vapor deposition process is of two types. One is chemical vapor deposition. Another one is physical vapor deposition. The physical vapor deposition is also again of 4 to 5 types there are 4 to 5 types of physical vapor depositions. So we'll see all this type of vapor deposition in the next or the subsequent classes. So this is for today actually. Do you have any questions?